A profound silence once filled the entire cosmos. Before the moon existed, before the Earth was even a dream, the universe was a vast and empty darkness. Then something miraculous happened. The first sparks of light flickered into existence. This is a journey to the very beginning, where we will uncover the 30 greatest mysteries surrounding the first stars and galaxies. We are living through a golden age of cosmic discovery, and by the end of this, you will understand how the universe woke up and how every atom in your body connects to that epic dawn. We will explore what made the first stars so unimaginably colossal and how their violent death seeded the cosmos with the ingredients for everything to come. What single question about our cosmic origins feels the most profound to you? That profound silence was broken by the very first generation of suns. These are not the stars we see today. Astronomers call them population 3 stars, and they were the universe's first experiment in lighting the darkness. Picture a star so immense it makes our sun look like a tiny speck. These primordial giants were made only from the pristine elements forged in the Big Bang, pure hydrogen and helium. They contained none of the heavier elements, the metals that exist in our sun and our planet and even in our bodies. This purity is the key to their first great mystery. How did they even form? In the modern universe, collapsing clouds of gas cool down by radiating heat away through dust grains and heavier molecules. That cooling allows the cloud to condense into a star, but the first clouds had no such help. They were simple, hot, and stubborn. So how did they overcome this to collapse into such behemoths? The leading theory suggests that vast amounts of gas had to collapse all at once, leading to stars of almost unimaginable scale. We think a typical population 3 star could have been hundreds of times more massive than our Sun. But was that the rule? Did they all form as solitary titans, or did they crowd together in the first fragile clusters? Their extreme mass dictated a ferocious and fleeting life. They burned through their nuclear fuel in just a few million years, a mere blink in cosmic time, and their deaths were just as spectacular as their births. When these pure hydrogen giants went supernova, the explosions were likely far more powerful and fundamentally different from any star death we can observe today. They completely obliterated themselves, scattering the first heavy elements, the seeds of future worlds, back into the void. But without any direct observations, their true nature remains one of cosmology's most compelling puzzles. These faint quantum ripples held the entire future of the cosmos in their grasp. In the deep dark that followed the Big Bang, the universe was a remarkably smooth and simple place. A vast, featureless sea of hydrogen and helium gas expanded into an absolute blackness, a period astronomers call the Dark Ages. There were no light sources, no beacons to break the monotony. Yet, woven into the fabric of this nascent cosmos were those tiny, primordial imperfections, slight variations in density that were the only seeds for everything to come. The great mystery is how these minuscule wrinkles could possibly grow into the colossal structures of the first stars. For gravity to pull a gas cloud together, it must overcome the outward pressure of the heated gas inside. In our modern universe, this is helped enormously by cosmic dust and heavier elements like carbon and oxygen. These act like a radiator, allowing the cloud to cool, shrink, and finally fragment into stars. But the first clouds had no such luxury. They were pure, pristine, and hot, with nothing to help them shed their intense thermal energy. So how did they ever collapse? Supercomputer simulations show us one possible path. They reveal that immense reservoirs of dark matter, the invisible scaffolding of the cosmos, began to pull the hydrogen and helium gas into its grasp. Within these vast, invisible wells, the gas could slowly, agonizingly condense. Without a way to cool efficiently, these clouds had to become incredibly massive before their own gravity could finally overcome the relentless internal pressure. We are talking about clouds containing the mass of hundreds of thousands of suns, collapsing into a single monstrous protostar. Visualize a supercomputer's rendering, a swirling, fiery maelstrom of gas in the absolute black, coalescing not into many small stars, but funneling its entire enormous bulk toward a single brilliant point. The process was likely slow and inefficient, a titanic struggle between the inward pull of gravity and the outward push of a hot, simple gas. This fundamental bottleneck makes the birth of that very first star one of the most difficult and majestic events to model in all of physics. These brilliant giants burned for only a few million years, and their light has been traveling for over 13 billion years to reach us. This creates the central observational challenge. The expansion of the universe has stretched their once fierce ultraviolet light into the far infrared part of the spectrum. It arrives as a faint cosmic whisper. Our most powerful eyes on the sky, like the James Webb Space Telescope, are specifically designed to listen for this whisper, yet the question remains, have we truly seen one? Astronomers are sifting through Webb's deep field images, looking for the telltale signature of a star made only of hydrogen and helium. The problem is that the very first galaxies, which formed soon after, can look deceptively similar. We might be looking at a brilliant early galaxy and not even realize a single colossal population 3 star is lighting it up from within. The hunt is not just for their light, but for the ghostly fingerprints they left behind. When these pure stars died in pair instability supernova, they should have left a unique chemical signature. They would have forged and scattered enormous amounts of specific elements like silicon and iron in a ratio unlike anything produced by later stars. Finding that pattern in the light of a distant quasar or etched into the spectrum of an ancient gas cloud would be indirect but powerful proof. To directly spot the light of a single first-generation star would be one of the greatest discoveries in the history of science. It would confirm our deepest theories about cosmic dawn and finally put a face to the entities that ended the universe's dark age. It is a Nobel Prize-level quest, a search for a ghost that illuminated the cosmos. The invisible architecture of the cosmos made the first stars possible. While the primordial gas was too hot and smooth to collapse on its own, it was drawn into the deep gravitational wells of dark matter. These vast, unseen halos acted as cosmic gathering points, providing the essential scaffolding for structure. Without them, the universe might have remained a formless, dark expanse forever. So what exactly were these first dark matter halos like? We believe they were relatively small and pristine, the very first knots to form in the cosmic web. They had to reach a critical mass, perhaps 1,000,000 times the mass of our Sun, before they could pull in enough gas to trigger that first miraculous collapse. But the nature of dark matter itself is the deeper puzzle. Was it cold, moving sluggishly and clumping together easily? Or was it warm, with faster moving particles that would have smoothed out the smallest clumps? The answer dictates the very timeline of cosmic dawn. If dark matter was cold, the first stars could have ignited surprisingly early. If it was warm, their formation would have been delayed, as it would take longer for smaller structures to form. This fundamental uncertainty means that by studying the first lights in the universe, we are actually probing the fundamental properties of the most elusive substance in existence. The distribution of those first brilliant points across the sky, a pattern we are only now beginning to map, holds the secret signature of dark matter itself. Pinpointing the exact moment the darkness broke is a challenge that spans the entire cosmos. When did that very first star begin to shine? Current evidence suggests the first flickers of light emerged around 200 million years after the Big Bang. But was this a singular event, one brilliant beacon switching on in the void? Or were there multiple, isolated points of light appearing across the vast cosmic expanse? The answer lies in understanding what happened next, a pivotal era called the epoch of reionization. For hundreds of millions of years, the universe was filled with a thick fog of neutral hydrogen gas. This fog was so effective at absorbing the energetic ultraviolet light from stars that it kept the entire cosmos opaque. But as more and more stars and early galaxies ignited, their intense radiation began to blast this fog apart, stripping electrons from the hydrogen atoms and turning them into a transparent, ionized plasma. This was reionization, the universe's great clearing. The central mystery is whether this was a swift and dramatic revolution or a slow and drawn-out dawn. Did the first stars flood the cosmos with light almost instantly, or was it a hesitant, patchy process where bubbles of transparency slowly grew and merged? The duration of this era is a key piece of the puzzle. Some models suggest it was all over in a relatively short few hundred million years, while others propose it was a more gradual affair. To solve this, astronomers turn to two powerful lines of evidence. The first is the cosmic microwave background, the afterglow of the Big Bang itself. By studying subtle patterns in this ancient light, we can measure the total amount of scattering caused by the leftover free electrons from reionization, giving us a rough bookend for when the process must have been completed. The second approach is to use telescopes like the James Webb to look back in time, counting the earliest galaxies and quasars we can find to see how many ionizing sources actually existed at different cosmic times. By combining these methods, we are slowly narrowing down the timeline, trying to capture the precise chronology of our universe's own enlightenment. These first stars did not simply fade away. They died in the most spectacularly violent events the universe has ever witnessed, and in doing so, they transformed the cosmos forever. Their deaths were not an end, but a fiery beginning. When a population 3 star, hundreds of times the mass of our Sun, reached the end of its brief life, its core became a frantic cosmic forge. For millions of years, it had been fusing hydrogen into helium, but now, in its final days, it began creating heavier elements in a desperate rush. Helium fused into carbon, carbon into oxygen, and so on, all the way up to iron. But iron is a dead end. Fusing iron does not release energy, it consumes it. With its energy source cut off, the star's core catastrophically collapsed. The resulting rebound unleashed a shockwave of unimaginable power, blasting the entire star apart in a supernova. This was not just any supernova. For the most massive of these primordial giants, theorists propose a far more exotic and total kind of destruction, a pair instability supernova. In this scenario, the core becomes so hot that light itself begins to transform. Photons of pure energy spontaneously convert into pairs of electrons and their antimatter counterparts, positrons. This process robs the core of the radiation pressure that was holding the star up. Without that support, the core collapses in a sudden, runaway implosion. The resulting thermonuclear explosion is so utterly complete that it completely unbinds the star. Every last bit of the star is vaporized and hurled out into space. There is no remnant left behind, no neutron star, no black hole. The star simply ceases to exist, leaving only an expanding cloud of newly forged elements. This leads to a profound mystery. Did all first stars die in this way, or did some of the slightly less massive ones leave behind the first black holes? The answer dictates the initial chemical makeup of the universe. A pair instability supernova would have scattered a unique cocktail of elements with a tremendous amount of iron relative to other metals. Finding that specific chemical fingerprint in the atmosphere of an ancient, second-generation star would be like finding the fossilized ash from one of these primordial explosions. This cosmic pollution was the essential next step. The pristine universe of only hydrogen and helium was now seeded with the ashes of the first stars, a dust of heavy elements we call metals. This metallic dust acted like a cosmic coolant. It allowed the next generation of gas clouds to fragment more easily, collapsing not into solitary behemoths, but into many smaller, more stable stars. The universe, for the first time, could create stars like our own Sun, stars capable of living for billions of years and nurturing planets. So every atom of oxygen you breathe, every particle of carbon in your body was forged in the heart of a long-dead star. But this stellar ash had to travel. How did these first heavy elements, the seeds of future life, spread from their explosive births to enrich the vast, empty reaches of space? The violent deaths of the first stars scattered the first metals into the void, but this was not the end of their story. It was the beginning of the next great cosmic construction project, the assembly of the first galaxies. How did these brilliant but isolated points of light evolve into the first structured collections of stars? The transition from a single, monstrous population 3-star to a cohesive galaxy is one of the most active puzzles in cosmology. Did a galaxy form around a single, brilliant titan, its gravity acting as a seed, or did many of these giants ignite almost simultaneously within a single, vast cloud of dark matter? The answer likely lies in a delicate and destructive dance. The first stars were not gentle neighbors. Their intense ultraviolet radiation blasted outward, heating the surrounding gas and pushing it away. Then, when they died in shattering supernova, they unleashed unimaginable shockwaves. This dual effect, known as stellar feedback, had two opposing possible outcomes. In one scenario, this feedback was purely destructive. The radiation and explosions could have blown the remaining gas cloud completely apart, ejecting the very fuel needed to form more stars and effectively sterilizing that pocket of the universe for millions of years. The first starburst would have been a flash in the pan, followed by a long, dark silence. But another, more intriguing possibility exists. The shock waves from those supernovae, instead of just destroying, could have acted as cosmic triggers. As these powerful waves compressed nearby clouds of pristine gas, they might have triggered a second wave of star formation. It is a cosmic paradox where destruction breeds creation. The expanding shells of debris from multiple supernovae could have collided, piling up gas into dense, cool layers that then fragmented into a new generation of stars. This generation would have been different, already containing a sprinkle of those first heavy elements. So did the first stars smother their own cradle or seed a nursery. The formation of the very first galaxy may have depended on a race against time. Could the dark matter halo pull in new, fresh gas from the cosmic web faster than the existing stars could blow it away? If so, a stable, ongoing star-forming environment could emerge, a true protogalaxy. We are now asking what the very first galaxy even looked like. Was it a tiny, dense spark containing just a few brilliant giants? Or was it a sprawling, chaotic factory, already birthing thousands of smaller stars from the polluted remains of its first generation? The James Webb Space Telescope is now peering back to this epoch, searching for these infant systems. Finding them is one thing, but understanding the violent birth pangs that shaped them is the true mystery we are only now beginning to solve. The violent deaths of those first stars may have planted the seeds for the most powerful and mysterious objects in the universe. At the heart of nearly every large galaxy today, including our own Milky Way, lies a supermassive black hole, a gravitational monster weighing millions or even billions of times more than our Sun. The greatest puzzle is not that they exist, but how they grew so immense so quickly. We have observed quasars, the intensely bright cores of ancient galaxies powered by these ravenous black holes, shining from an era when the universe was less than 1 billion years old. For a black hole to reach 1 billion solar masses in that short time feels almost impossible. It is a cosmic race against the clock that current models struggle to explain. How did they get so big, so fast? The answer might lie directly with the first generation of stars. One compelling theory points to the direct collapse of supermassive gas clouds in the early universe. Imagine one of those pristine clouds of hydrogen and helium, but instead of fragmenting into many stars, something prevents it from breaking apart. Perhaps it was the intense ultraviolet light from a nearby population 3 star, bathing the cloud in radiation and keeping it too hot to split. This single monstrous cloud, containing the mass of hundreds of thousands of suns, could then collapse in on itself all at once. It would bypass the star-making stage entirely, plummeting directly into a colossal black hole, a ready-made heavyweight from its very first moment. This is a direct collapse black hole, a theoretical giant born not from a star's death, but from a primordial cloud's failure to become one. Another path involves the remnants of the first stars themselves. If a population 3 star was massive enough, but not quite in the pair instability range, its core collapse could have left behind a black hole of a few hundred solar masses. In the dense, crowded environments of the very first protogalaxies, these black hole seeds could have sunk to the center, merged with one another, and begun a frantic feast on the surrounding gas. This rapid merging and feeding could have allowed them to snowball in size at a staggering rate. Which path did nature prefer? Did the first galaxies build their central monsters from a single, enormous seed, or from a swarm of smaller ones that consolidated their power? The light from those ancient quasars holds the answer, a faint echo of a feeding frenzy that began with the very first starlight. The light from a brilliant quasar acts as a cosmic probe on its journey to our telescopes. As this beam travels for billions of years, it passes through countless clouds of neutral hydrogen gas, the primary component of the early universe. Each time it encounters one of these clouds, a specific color or wavelength of light is absorbed, corresponding to the Lyman-alpha transition of hydrogen. The result is a spectrum that looks like a dense, intricate forest of absorption lines. Each individual line is a tree, representing a single cloud of gas intersecting the quasar's line of sight. The sheer density of this forest reveals an astonishing truth. It shows us that the early universe was not a smooth, empty void, but was already filled with a complex, web-like structure of hydrogen, a cosmic scaffolding upon which galaxies would later be built. But the mystery deepens with the clearings in this forest. As astronomers analyze these absorption lines, they find gaps, regions where the hydrogen absorption suddenly disappears. These are not empty voids, they are the imprints of colossal bubbles, regions where the intense radiation from the first stars and galaxies has blasted the hydrogen apart, ionizing it and rendering it transparent. The size and distribution of these bubbles, seen as voids in the Lyman-alpha forest, are a direct fossil record of the epoch of reionization. Were these bubbles small and isolated at first, indicating a few scattered sources of light? Or were they already vast and overlapping, suggesting a universe flooded with ionizing radiation surprisingly early? The pattern of the forest tells a story. By studying the clustering of the absorption lines, astronomers can infer the gravitational pull of the dark matter halos that hosted the earliest structures. A highly clustered forest suggests that the first galaxies themselves were already strongly grouped together, painting a picture of a universe where structure formed quickly and decisively. It is a form of cosmic cartography, using a single beam of ancient light to map the distribution of both visible and dark matter across billions of light years. This ghostly forest, imprinted on quasar light, is one of our most powerful windows into an era we can never directly see, revealing the architecture of the cosmos as it was under construction. Our cosmic neighborhood holds a ghost story. The vast halo of our Milky Way should be swarming with thousands of ancient dwarf galaxies, small and faint relics from the earliest days of structure formation. Powerful supercomputer simulations tell us this should be the case. These simulations trace the evolution of the universe from its smooth beginnings, showing how dark matter clumped first into tiny halos. These small halos were the building blocks, the very first structures to emerge from the cosmic dark ages. They should have pulled in gas and ignited their own first stars, becoming tiny primordial galaxies. And according to the models, thousands of these fossil galaxies should still be orbiting our own. But when we look up at the sky, we find only a few dozen. The vast majority are missing. This is the core of the missing satellite problem, a glaring mismatch between our theoretical predictions and what we actually see. So where did all the satellites go? One possibility is that star formation in the very smallest dark matter halos was incredibly inefficient or even impossible. The ultraviolet background radiation that flooded the universe after reionization could have heated the gas in these tiny halos, preventing it from cooling and collapsing to form stars. These halos would still be out there, dark and invisible, made only of the mysterious dark matter, their stellar potential forever unfulfilled. Another idea is that the first stars did form in these small halos, but their light was just too faint for us to easily detect. Our surveys may simply be missing a hidden population of extremely faint and diffuse dwarf galaxies, but the most profound possibility is that this discrepancy is pointing to a fundamental flaw in our understanding. Perhaps our models for dark matter are incomplete. The standard cold dark matter model works beautifully on large scales, but what if dark matter behaves differently on the small scales of these dwarf halos? If dark matter were slightly warm, meaning its particles moved faster, it would not clump as easily into such small, dense structures. This would naturally lead to fewer small halos, neatly solving the missing satellite problem. Or perhaps the physics of star formation in these tiny, pristine environments was so unique that our simulations are not capturing it correctly. Maybe supernova feedback in these fragile systems was so violent that it blew all the gas out, permanently shutting down star formation and leaving behind a dark, barren halo. This mystery connects the grand story of cosmic dawn directly to our own galactic backyard. The absence of these expected fossils is a powerful clue, telling us that the final chapter on the first structures has not yet been written. These faint, ghostly galaxies are the silent survivors from the dawn of time. Drifting in the vast halo of our Milky Way are the ultra-faint dwarf galaxies, cosmic relics so dim that they were hidden from us until very recently. They contain only a few thousand stars lost in the immensity of space. Their profound dimness is the very reason they are so precious to astronomers. They are living fossils, pristine time capsules that have remained virtually unchanged for over 13 billion years. The central mystery they present is why their star formation shut down so abruptly and so early. It is as if they were born, experienced a single, brief burst of stellar creation, and then fell into a deep cosmic sleep, preserving their ancient state for eons. What could have caused such an abrupt halt? The leading suspect is the very event that cleared the cosmic fog, the epoch of reionization. As the first brilliant galaxies flooded the universe with ultraviolet radiation, this intense background light would have heated the sparse gas inside these small, fragile dwarfs. Their gravitational grip was too weak to hold onto this heated gas. It was likely boiled away and blown out into intergalactic space, robbing the dwarfs of the raw material needed to make new stars. This left them frozen in time, their stellar populations forever stunted. But an even deeper mystery lies in the composition of the stars within them. Do these faint galaxies contain stars that are almost entirely metal-free, the direct descendants of the first population 3 stars? Finding a true second-generation star, one forged from the pure, unmixed ashes of a single primordial supernova, would be the ultimate prize. It would be like finding a perfectly preserved archaeological sample from the universe's first chemical forge. The search is incredibly difficult, as it requires analyzing the faint light from individual stars in these already dim galaxies. Each spectrum is a delicate operation, a search for a chemical signature of unprecedented purity. Why did some of these early systems fail to grow into large galaxies like our own? The answer may lie in their birth environment. Perhaps they formed in small, isolated dark matter halos that were simply left behind as the cosmic web evolved, starved of fresh gas from the very beginning. Studying these galactic fossils is like conducting the most delicate archaeological dig on a cosmic scale. They offer us a potential direct window into the conditions of the very first structures, a glimpse of a simpler universe frozen in its infancy. But if these are the preserved building blocks of larger galaxies, how did those larger structures, the true ancestors of galaxies like our Milky Way, actually take shape from such humble beginnings? Solving the mystery of reionization means identifying the primary architects of this cosmic transformation. Who or what provided the overwhelming flood of ultraviolet radiation that stripped electrons from atoms across the entire universe? The suspects are compelling. The first and most obvious are the massive population 3 stars. A single one of these primordial giants could outshine a small galaxy, and their intense ultraviolet light would have been perfectly tuned to ionize hydrogen. But their lives were incredibly short. Could such brief, brilliant flashes have sustained a universal reionization, or were they merely the first sparks? The second suspect is the collective output of the first galaxies. While an individual early galaxy might have been less potent than a single population 3 star, their growing numbers could have provided a steady, rising tide of ionizing photons, gradually flooding the cosmos with transparency. Then there is the third, more exotic suspect, accreting black holes. The first quasars, with their searingly bright accretion disks, are incredibly efficient at producing ionizing radiation. But were they numerous enough to contribute significantly, or were they just rare, brilliant beacons in a sea of stellar light? The answer likely lies in a cosmic collaboration, but determining the lead actor is crucial. This is where the James Webb Space Telescope enters the investigation with a specific mission: to measure the leakiness of the earliest galaxies. For a galaxy to contribute to reionization, its ionizing photons cannot be trapped within it. They must escape the galaxy's own gaseous cocoon and travel into the vast intergalactic medium. If a galaxy's gas is too dense, it will absorb these photons itself, like a fog bank swallowing a lighthouse beam. Webb is now analyzing the spectra of galaxies from this epoch, searching for specific telltale signs that a significant fraction of their most energetic light is in fact leaking out. The amount of this escaping radiation is the key number that will tell us if early galaxies were the primary drivers. Finding that they were very leaky would point the finger squarely at them. If they were mostly sealed, however, the mystery deepens, forcing us to reconsider the role of those first, fleeting stellar titans or the power of the earliest black holes. We are closing in on the source of the light that cleared the cosmic fog. That precise moment of first light marks a fundamental boundary in cosmic history. We can calculate when it likely happened, but we cannot know the exact scene that unfolded. Was it a singular event, one magnificent superstar switching on in an ocean of black, its light beginning a lonely journey through a neutral gas that had never known such an intrusion? Or was the universe already subtly patterned, with a handful of these beacons flickering into existence within a short cosmic time of one another, like the first few lights in a city waking up at dawn? This is not just a question of timing, it is about the very nature of the cosmos's transition. Before that moment, the universe was a remarkably simple place, governed by the smooth expansion from the Big Bang and the gentle pull of gravity on dark matter. It was a monologue of physics. The ignition of the first star changed everything. It introduced a powerful new character, one that could transform its environment. That first star did not just illuminate the void, it began to fundamentally alter it. Its intense ultraviolet radiation started to cook the surrounding hydrogen gas, creating a growing bubble of hot, ionized plasma within the vast, cold neutral fog. This was the first wound in the Dark Ages. Think of the universe at that instant as a vast, dark sheet of paper, and the first star as a hot brand pressed against it. The immediate area around the brand is scorched and changed forever. But was there just one brand, or were there several, held at different distances, beginning to burn their own separate marks? The answer defines the beginning of reionization. A single, isolated beacon would have created a single, expanding bubble of transparency. A cosmos with multiple, near-simultaneous ignitions would have looked like a sheet of paper with many small, scattered burns that slowly grew and merged. The transition from a dark to a lit universe was not like flipping a master switch for a whole city. It was likely a hesitant, patchy process where islands of light slowly conquered a sea of darkness. This first chapter of light set the stage for everything that followed. It was the moment the universe gained the ability to create complexity, to forge new elements, and to eventually set the conditions for life. The nature of that very first dawn, whether it was a solitary sunrise or a scattered cosmic glitter, remains one of the most profound and elusive mysteries in all of science. The very first generation of stars holds a secret locked within their birth weights. Astronomers call this the initial mass function, a technical term for a simple but profound question. When those primordial clouds collapsed, what sizes of stars did they make? Did they create only colossal titans, hundreds of times heavier than our Sun? Or was there a full spectrum of sizes, including smaller, longer-lived stars that might still be shining faintly in some forgotten corner of the cosmos? The answer to this single question dictates everything that followed the cosmic dawn. A universe dominated by solitary behemoths would have had a very different early history than one filled with a diverse population of stars. The life and death of a star is a direct consequence of its mass. A star 100 times the mass of the Sun lives a frantic, brilliant life for only a few million years before dying in a cataclysmic supernova. It forges and scatters a specific set of heavy elements in a single, enormous blast. But a smaller, 50 solar mass star would live longer and die a slightly different death, producing a different chemical yield. And a star just 20 times the mass of our Sun could survive for tens of millions of years, potentially leaving behind a black hole instead of completely vaporizing itself. Each of these scenarios seeds the next generation with a distinct chemical fingerprint. So how do we solve a mystery about stars that have been dead for over 13 billion years? We become cosmic detectives looking for clues in the oldest stars we can find. Within the faint light of ancient second-generation stars, we can read the chemical abundances etched into their atmospheres. These stars formed from gas polluted by the very first supernova. Finding a star with an unusual chemical pattern, one rich in zinc and cobalt but surprisingly poor in iron, could be the smoking gun for a pair instability supernova from a true behemoth. Other chemical signatures might point to the more muted death of a smaller giant. The challenge is that these chemical fossils are incredibly rare and difficult to interpret. Supercomputer simulations offer another line of evidence, allowing us to test different theories of star formation. When we model the collapse of a pristine, metal-free cloud, the results are startling. Many simulations show that without metals to cool the gas efficiently, the cloud struggles to fragment. It tends to funnel its entire mass into one or just a few truly massive stars. This supports the idea of a top-heavy initial mass function skewed heavily toward the giants, but newer, more complex simulations hint at a different possibility. They suggest that under certain conditions, like rapid rotation or intense turbulence, even a pristine cloud could break up into a cluster of stars with a wider range of masses. Perhaps the first star factories did not just produce lonely kings, but entire royal courts of stars of varying sizes. The implications are staggering. If even a small fraction of the first stars were of lower mass, some of them might still be alive today. Finding such a star would be the ultimate discovery, a living witness to the universe's infancy. The hunt is on, a meticulous sifting of starlight for a chemical composition of pure hydrogen and helium, a relic from a time before time. The initial mass function is not just a dry statistical curve. It is the genetic code for the universe's first steps toward complexity. determining the speed and the pathway by which our cosmos became the rich, structured place it is today. The lonely giant model of the first stars is now being challenged by a fascinating possibility. Could the universe's first lights have been born with companions? The question of whether binary star systems existed in the primordial cosmos is not just academic. It reshapes our entire understanding of early structure and the origins of the gravitational waves we detect today. In our modern galaxy, most massive stars are born in pairs or small groups. Their formation relies on a gas cloud's ability to cool, fragment, and collapse into several distinct cores. But that process is helped enormously by the presence of cosmic dust and heavy elements, which the first clouds completely lacked. Without these efficient cooling agents, how could a single, massive cloud possibly break apart? The answer might lie in a more chaotic and dynamic birth. New, high-resolution supercomputer simulations are revealing that the accretion disks feeding the growth of a massive protostar can become gravitationally unstable. As immense amounts of gas spiral inward, the disk itself can develop ripples and clumps. These clumps, if they become dense enough, could potentially collapse under their own gravity to form a second or even a third stellar companion. Instead of a single star hoarding all the gas from its entire cloud, the system might form a small, multiple family of stars all vying for the same reservoir of fuel. This is a fundamentally different path to binary formation than we see today. The resulting pairs would likely have been extremely tight, orbiting each other in a furious dance, and both would still be colossal, true siblings in mass and scale. The implications of such early binaries are staggering, especially for their ultimate fates. If two such massive stars are born as a bound pair, and each one collapses into a black hole at the end of its life, you have the perfect ingredients for a future cosmic event. These first black holes would be the primordial seeds for mergers. They would slowly spiral inward over billions of years, their orbits decaying through the emission of gravitational waves until they finally collided in a violent union that shook the fabric of spacetime itself. This creates a direct, tangible link between the first flickers of light and the ripples in spacetime that our observatories like LIGO and Virgo are detecting today. Every black hole merger we see could have a lineage that stretches all the way back to a pair of massive twins born in the cosmic dawn. Finding evidence for this is incredibly difficult but not impossible. The light signature of a distant, early binary system would be complex and shifting, a potential clue hidden in the data from the most powerful telescopes. Confirming that the first stars had companions would completely rewrite the final chapter in their life cycle, turning solitary deaths into a coordinated dance of darkness that still echoes across the universe. A hidden cosmic force might have guided the hands of creation itself. Just as the first clouds of pristine gas began their long collapse, they could have been threaded with an invisible web of magnetism. The question of primordial magnetic fields is one of the most subtle and complex puzzles in early cosmology. Were these fields present from the very beginning, woven into the fabric of spacetime during the universe's first frantic moments, or were they born later, generated by the first turbulent motions of ionized gas? Their existence, or lack thereof, could have fundamentally altered the blueprint for the first stars. In a modern star-forming cloud, magnetic fields act as a cosmic support structure. They provide pressure that fights against gravity's pull, slowing the collapse and helping to transfer angular momentum away from the central core. This process allows a cloud to spin down and fragment into multiple stars. But in the very first clouds, devoid of the dust and metals that help modern fields couple efficiently to the gas, how would a magnetic field have behaved? A weak, primordial field might have been too feeble to have any significant effect, its influence drowned out by the immense thermal pressure of the hot hydrogen and helium. But a stronger field could have been a dominant player. It might have provided just enough extra support to prevent a cloud from fragmenting, channeling the entire flow of gas into the formation of a single, even more massive star than we currently predict. Alternatively, a tangled dynamic field could have done the opposite. By helping to shed the cloud's spin, it might have actually encouraged the disk around a growing protostar to break apart, fostering the birth of a binary or multiple star system instead of a solitary titan. This single variable, the strength and structure of the earliest magnetism, could be the key that determines whether the first stellar nurseries produced lonely monarchs or crowded families of giants. We have no direct way to observe these ancient fields, but their ghostly signature might be imprinted in the cosmic microwave background or inferred from the clustering of the very first galaxies we are now discovering. Unraveling this mystery requires a deep dive into the strange marriage of gravity and plasma physics, a union that may have written the very first rules for how a dark universe learned to build its lights. The violent dance of the first binary stars could still be echoing across the cosmos. We have been exploring the dawn of time through the faintest traces of ancient light, but what if we could listen to it as well? Gravitational wave astronomy opens this entirely new sense. These are not ripples of light or radiation, but literal vibrations in the fabric of space-time itself, generated by the most cataclysmic events in the universe. When two massive objects, like the black hole remnants of the first stars, spiral inward and merge, they shake the cosmos, sending out waves that travel at the speed of light. The ground-based observatories LIGO and Virgo have already begun to hear these cosmic rumbles from more recent black hole mergers, but to listen for the very first ones, we need to go to space. The Laser Interferometer Space Antenna, or LISA, is a future observatory designed to do exactly that. Imagine 3 spacecraft flying in a perfect triangle millions of miles apart, connected by lasers. They would form the most sensitive listening device ever built, a gravitational wave telescope free from the seismic noise of Earth. What would LISA be listening for? It would hunt for the low-frequency hum of supermassive black hole mergers, the grand finales of galaxy collisions. But more importantly for our story, it could also detect the mergers of those first, smaller black holes, the ones that might have formed from primordial binary star systems. This would be a direct, unmediated signal from the cosmic dawn. Think of it this way. Light from the first stars can be absorbed, scattered, and red shifted into near invisibility by the gas and dust it passes through over billions of years. It is a message that has been degraded and corrupted on its long journey to us. A gravitational wave, however, passes through matter almost completely unaffected. It is a pure, clean signal, detecting the gravitational wave chirp from the merger of 2 100 solar mass black holes that formed just a few 100 million years after the Big Bang would be like overhearing a private conversation from the beginning of time. This data would be revolutionary because it is complementary to what telescopes see. A telescope like James Webb might show us the light from an early galaxy, telling us about its stars and gas. LISA could tell us about the invisible dance of the monster black holes at its heart, or the mergers of its stellar building blocks. It would provide a census of the first black holes, revealing their masses and how common these binary systems truly were. Were the first stars mostly solitary, leaving behind isolated black holes, or were they born in pairs, creating a universe filled with the potential for these ancient, space-time shaking mergers? The answer is written in gravitational waves, a hidden chapter of cosmic history waiting to be heard. A faint, all-pervading glow fills the spaces between the galaxies. This is the cosmic infrared background, a diffuse light that bathes the entire universe. It is not the sharp, pinpoint light of individual stars or galaxies we are used to seeing. Instead, it is a collective whisper, the combined, unresolved output of countless sources too dim and distant for even our best telescopes to pick out one by one. Think of it like standing in a vast, dark field at night and seeing the distant glow of a city on the horizon. From your vantage point, you cannot make out individual streetlights or windows, but the collective glow tells you without a doubt that a massive, populated center lies ahead. The cosmic infrared background is that same glow on a universal scale, and a significant part of it is the accumulated light from the very first stars and galaxies, stretched and reddened by the expansion of the cosmos over billions of years. The central mystery is how to decode this faint signal. Can we tease apart the specific contribution of those first pure population 3 stars from the light of later generations? The pattern of this background light is a fossil imprint of the total star formation activity during the cosmic dawn. If the first stars were incredibly numerous and bright, they would have left a strong, distinctive signature in this infrared fog. If they were rarer, their contribution would be fainter, lost in the chorus of light from later galaxies. Astronomers are like detectives trying to identify a single voice in a vast, ancient choir. They use sophisticated statistical tools to analyze the fluctuations in this background glow, looking for subtle clumping or specific patterns that might be the unique calling card of population 3 stars. Finding that signature would allow us to census these elusive giants, to finally understand how many of them truly existed and how they were scattered across the early cosmos. Were they evenly distributed, or did they cluster in specific bright knots that correspond to the first dark matter halos? The answers are written in this dim, universal light, a final, integrated picture of the universe's first illumination. These first supernovae did more than just scatter new elements, they forged the very dust that would cool the cosmos. In the aftermath of those titanic explosions, as the expanding clouds of stellar debris cooled, atoms began to cling together in the hostile vacuum of space. Carbon, silicon, and iron atoms collided and stuck, forming the first microscopic solid particles, the very first dust grains in the universe. This was not the fine, complex dust we see today, rich with silicates and carbon compounds. This primordial dust was likely a crude, hardy soot, but its role was absolutely critical. Dust grains are phenomenally efficient at radiating away heat. When a single dust grain is struck by a photon of light, it vibrates and re-radiates that energy away as infrared light, effectively acting as a cosmic air conditioner for a gas cloud. This is the second great mystery of the transition. The first stars lit up the universe and their deaths polluted it with metals, but it was this newly formed dust that provided the crucial cooling mechanism the pristine universe so desperately lacked. Without dust, those second-generation gas clouds, now enriched with metals, would still have struggled to cool and collapse. The dust gave gravity the upper hand, allowing clouds to fragment into many smaller, more stable stars like our own sun. So where did this foundational dust primarily come from? Was the factory floor exclusively the violent ejector of pair instability supernova? These total explosions would have blasted out a tremendous volume of heavy elements, creating perfect conditions for dust to condense as the expanding fireball cooled. Or did another, slower source contribute significantly? Another possibility lies in the later stages of slightly less massive but still enormous early stars. As these stars aged, they could have blown off their outer layers in powerful stellar winds. In the relative calm of these winds, away from the violence of a supernova shockwave, atoms could have found each other and condensed into dust grains more efficiently. The composition of the dust holds the answer. Supernova-sourced dust would be rich in elements like silicon, magnesium, and iron. Dust from carbon-rich stellar winds would be dominated by graphite and other carbon compounds. We are searching for the chemical fingerprint of this first dust in the most ancient light we can observe. The James Webb Space Telescope is now analyzing the spectra of incredibly distant galaxies, looking for the telltale absorption signatures of these early dust grains. Finding an ancient galaxy that already appears dusty pushes our models for how quickly dust factories could have started operating. Did the universe become dusty almost immediately after the first stars died, or was it a more gradual accumulation? The timeline of dust production is the hidden clock that set the pace for the universe's transformation from a realm of giants to a cosmos capable of building long-lived stars and the planets that orbit them. The brilliance of the first galaxies is not a simple matter of size. We are now confronted by a deep puzzle. Were these infant systems blazing beacons, their light dominated by a few ferociously luminous population 3 stars, or were they relatively dim, sprawling collections of smaller, more ordinary suns? Their brightness or luminosity is a direct window into their inner workings, revealing their star formation rates and the kinds of stars that lived and died within them. For years, cosmological models painted a picture of a hesitant dawn where the first galaxies were small, faint, and slow to build. Then the James Webb Space Telescope began to look, and it saw something astonishing. It found galaxies that are shockingly bright and remarkably evolved at impossibly early times, when the universe was a mere 300 or 400 million years old. These are not the faint, fragile sparks we expected. They are cosmic toddlers with the muscle of giants. How could such well-structured, luminous systems assemble so quickly after the Big Bang? This discovery strikes at the heart of our understanding of structure formation. It forces us to ask if the first bursts of star formation were far more intense and efficient than we ever dreamed. Perhaps the first dark matter halos pulled in gas with a ferocious appetite, creating starbursts of incredible power. Or maybe the initial mass function in these galaxies was wildly top-heavy, producing a disproportionate number of those brilliant, short-lived giants whose collective light would outshine anything we see in the modern universe. Another tantalizing possibility is that these early galaxies are not just bright from starbirth, but from something else entirely. Could the light we see be amplified by the brilliant accretion disks of the first supermassive black holes, already active and shining at the hearts of these young systems? Each explanation carries profound implications. If it was a frenzy of star formation, then the early universe was a far more violent and productive place than our simulations predicted. If it was the light of early black holes, then the seeds for these monsters must have formed almost instantly with the galaxies themselves. The James Webb Telescope is now acting as a cosmic detective, analyzing the spectra of these unexpectedly bright galaxies. By breaking their light down into a rainbow of colors, astronomers can search for the telltale chemical signatures that reveal their true nature. Are their spectra dominated by the features of massive hot stars, or do they show the broad emission lines characteristic of a voracious black hole? The answer is not yet clear, and that is the core of the mystery. The sheer luminosity of these first galaxies is a direct challenge, a brilliant question mark written across the early sky that forces us to reconsider the very pace at which our universe woke up. The primordial gas was a chaotic sea long before the first stars took shape. Turbulence, the random, churning motion within these ancient clouds, is a fundamental force that both builds and resists. It is the great paradox of star birth. On one hand, turbulence can be a creator. When supersonic waves crash through a gas cloud, they act like cosmic tsunamis, compressing the gas into dense, tangled filaments and knots at their collision points. These shock-induced overdensities become the perfect seeds for gravity to take hold, creating the initial conditions for a protostar to form. Yet, in the very same breath, turbulence is a preserver. All that churning motion generates a powerful outward pressure, a kind of kinetic energy that fights against gravity's relentless inward pull. It can keep a cloud puffed up and stable, preventing it from collapsing altogether. So, which effect dominated in the first clouds? The answer is buried in the physics of a universe without landmarks. This was not the gentle turbulence of a cloudy sky. It was likely supersonic, chaotic motion driven by the gravitational pull of dark matter and the explosive feedback from the very first supernova. The gas was not calm. It was a roiling, violent medium, but without metals or dust to help it cool, this turbulence might have been mostly hot air, all motion and heat with no way to settle down. The critical unknown is the virial parameter, a measure of this balance between turbulent energy and gravitational potential energy. Was the turbulence just enough to seed collapse but not so much as to prevent it? Our most advanced simulations show that even a slight change in this initial turbulence can dramatically alter the outcome. A highly turbulent cloud might fragment into a small cluster of massive stars, while a calmer, quieter cloud could funnel its entire mass into a single, unbelievable giant. The level of that first chaos, therefore, set the blueprint for everything that followed. It decided whether the cosmic dawn was illuminated by solitary beacons or by glittering clusters. This is not a minor detail in our models. It is a core uncertainty that means we are still guessing at the very texture of the universe's first structures. Could the universe's first stars have been the center of alien planetary systems? This question pushes our imagination to its limits. We know that population 3 stars were made of only hydrogen and helium with no heavier elements, the very stuff that rocky planets like Earth are built from. So how could a planet possibly form in such a pristine environment? The answer might lie in a different kind of world entirely. Some astrophysicists theorize that gas giant planets, similar to Jupiter, could have coalesced directly from the swirling disk of primordial gas that fed the growing protostar. In this scenario, gravity would cause clumps of pure hydrogen and helium to collapse within the disk, potentially forming vast, puffy worlds without a solid core. These would not be planets as we understand them. Imagine a world with no rock, no metal, no sand or stone. It would be a deep, swirling ball of gas all the way to its center, a world with no surface to stand on. Its atmosphere would be a featureless, perpetual fog of hydrogen, perhaps with occasional rain of liquid helium, a landscape of unimaginable simplicity. The skies above such a world would be just as strange. By day, the planet would be bathed in the intense, unforgiving ultraviolet light of its colossal parent star. There would be no gentle yellow sunlight, and by night the sky would be an absolute, unbroken blackness, devoid of any other stars or galaxies, for the cosmos was still in its dark ages. The existence of even one such planet would force us to rewrite the history of planet formation. It would mean that the seeds of cosmic architecture were planted far earlier than we ever thought possible. But these worlds would have been tragically short-lived. When their massive star died in a cataclysmic supernova, any orbiting planets would have been utterly vaporized in the blast, their material scattered and mixed with the new heavy elements to become part of the next generation. They were fleeting, ghostly kingdoms in the dark, the first and most alien planetary experiments that the universe ever conducted. Our view of the cosmic dawn is like looking at a single grain of sand to understand an entire beach. We can only observe a finite volume of the early universe, a bubble of space-time defined by how far light has been able to travel to us in 13.8 billion years. This creates a fundamental problem called cosmic variance. The great mystery is whether our little pocket of observation is truly typical, or if we are just seeing one quiet neighborhood in a cosmos filled with wildly different districts. Imagine the universe just a few 100 million years after the Big Bang. In our observed patch, the first stars might have been slow to ignite, their formation delayed by local conditions. But in another region, just beyond our observational horizon, a spectacular fireworks display could have already been underway, with countless brilliant giants flooding the void with light far earlier. We have no way of seeing that other region. Its light has not had time to reach us, and it never will due to the accelerating expansion of the universe. That part of cosmic history is forever lost to us, so when our telescopes count the number of early galaxies in our field of view, how do we know if that number is average? What if we are simply in a cosmic underdense region, a quiet suburb of the early universe, while other areas were dense, glittering metropolises? This variance makes it incredibly difficult to draw universal conclusions. A measurement from one direction might suggest a slow, gradual dawn, while a measurement from another might hint at a surprisingly rapid awakening. We are like astronomers on a foggy island, trying to determine the climate of the entire planet by only looking at the weather in our own backyard. This uncertainty touches every aspect of the early universe. Did reionization happen uniformly, or was it a patchwork process where some bubbles of transparency grew vast while others lagged behind? The answers we seek about the very first stars and galaxies might be fundamentally limited by our own location in space and time. We are left to wonder if the story we are piecing together is the universal epic of creation or merely a local folktale. Deep within our own cosmic neighborhood, ancient stars hold chemical memories of a time long before the Earth existed. These stellar fossils allow astronomers to perform a kind of galactic archaeology, digging through the atmospheres of the oldest stars to uncover the properties of their long-dead progenitors. A star known as He075240 is one of these precious relics. Its spectrum reveals an almost unimaginable poverty of heavy elements, possessing less than 1/200,000th the iron found in our Sun. This extreme metal deficiency marks it as a genuine second-generation star, one of the very first to form from the polluted ashes of the universe's initial supernova. The composition of such a star is not a random mixture. It is a specific chemical fingerprint, a unique recipe forged in the single, violent death of a population 3 star. By analyzing this fingerprint in exquisite detail, scientists can work backwards to reconstruct the life and death of that first star. The precise ratios of elements like carbon, oxygen, and magnesium act as a cosmic autopsy report. A high abundance of carbon relative to iron, for instance, might point to the specific nuclear fusion processes that occurred inside a 200 solar mass giant. The overall low yield of iron could indicate the star died in a peculiar pulsational supernova that only ejected its outer layers. Each elemental ratio is a clue. This detective work is incredibly complex because the chemical pattern we see is the result of the original star's mass, its internal rotation, the energy of its explosion, and even the dilution of its ejector with pristine interstellar gas. It is like hearing a single, faint echo and trying to deduce the exact size, shape, and material of the bell that created it from 13 billion years ago. Yet, by comparing the observed chemical signatures of stars like He075240 with vast libraries of theoretical supernova models, astronomers are narrowing down the possibilities. They are beginning to identify the mass range of the first stars and understand the exotic ways in which they died. This stellar archaeology transforms these faint points of light in our galactic halo into direct messengers from the cosmic dawn, each one telling the story of a single, monumental explosion that helped end the universe's dark age. The final moments of a first star were a cosmic lottery with profound consequences. Its death did not always lead to the same outcome, and the nature of its remnant became a foundational legacy for the evolving universe. For the very largest of these primordial giants, those in the pair instability mass range, death was total. The thermonuclear explosion was so utterly complete that it left absolutely nothing behind. The star was entirely vaporized, its material scattered as an expanding cloud of new elements. But what about those that were slightly less massive? If a population 3 star fell below a certain threshold, perhaps around 140 solar masses, its core collapse could have resulted in a different fate. The implosion would have been so violent that it bypassed the formation of a neutron star entirely, collapsing directly into a black hole. This creates a direct lineage. The very first stars, born with hundreds of solar masses, could have sown the cosmos with the very first stellar mass black holes, each one a gravitational pit of several dozen or even 100 times the mass of our Sun. The initial mass function of those first stars, therefore, directly dictated the initial population of these dark seeds. If most first stars were true behemoths that completely disrupted themselves, the early universe would have been relatively empty of black holes. But if a significant number were in the right mass range to leave a remnant, then the cosmic dawn would have been followed by a twilight filled with these invisible anchors. These first black holes were not the end of the story, but the beginning of a new one. They were the primordial stock for future growth. In the dense environments of the first protogalaxies, these black holes could have sunk to the center, merged with one another, and begun to accrete gas at a ferocious rate. They were the potential seeds for the supermassive black holes we find at the hearts of galaxies today. Furthermore, if many of these first stars were born in binary pairs, as some theories suggest, then their black hole remnants would have been destined for a future merger. The gravitational wave chirps we detect from black hole collisions today could be the distant echoes of these first stellar deaths, a cosmic signal from an era of pure, massive giants. The fate of the first star's remnants is not just a question about the past. It is the key to understanding the dark population that still lurks in our cosmos and the gravitational rumbles that quietly shake the fabric of spacetime. The faint echo of a cosmic drumbeat may have guided the placement of the first lights. Before there were stars or galaxies, the universe was a seething plasma, a dense and hot soup of particles and light. In this primordial fluid, pressure waves rippled outward, vast sound waves traveling through the infant cosmos. When the universe cooled enough for atoms to form, allowing light to travel freely, these waves were frozen in place, imprinting a subtle pattern onto the distribution of matter. This fossilized imprint is what astronomers call baryon acoustic oscillations, a preferred scale woven into the fabric of the cosmos. Imagine a single, unimaginably large ripple in a pond, and then freezing the pond solid at that exact moment. That is the essence of the baryon, a standard ruler etched across the sky. The great mystery is how this vast, large-scale pattern, spanning hundreds of millions of light years, could possibly influence the small-scale, local process of the first star formation. Did those first, brilliant points of light simply ignite at random, or were they drawn to specific locations along these ancient cosmic ripples? The baryon created a subtle web of overdensities, regions where matter was ever so slightly more concentrated. In the long collapse toward the first stars, could these gentle gravitational hills have given a tiny head start to gas clouds falling into them? It is a question of scale versus locality. The formation of a single population 3-star was a violent local event, a battle between gravity and thermal pressure in a single cloud. But the distribution of those clouds across the universe may not have been random. The baryon pattern could have acted as a cosmic template, a faint blueprint that made it statistically more likely for the first structures to emerge along the crests of those frozen waves. This would mean the first stars did not light up uniformly, but in a grand, subtle architecture that reflected the universe's own earliest vibrations. We are now searching for this pattern in the maps of the most distant galaxies, looking for a faint whisper of correlation between their positions and the primordial oscillations. Finding that link would be profound. It would connect the fiery birth of the first stars directly to the physics of the Big Bang itself, revealing that the universe's first structures were orchestrated by a rhythm set in motion at the very beginning of time. The temperature of the primordial gas was the critical factor that decided everything. Before the first star could ignite, its parent cloud had to surrender its heat, cooling down enough for gravity to finally win its long battle. But without any of the complex molecules or dust grains that help modern clouds cool, how did the first gas shed its energy? The universe had to rely on a single, rudimentary coolant, molecular hydrogen. This simple molecule, just 2 hydrogen atoms bound together, was the only thing standing between a hot, formless cloud and the birth of a star. Its formation, however, was a cosmic bottleneck. In a sea of solitary hydrogen atoms, getting two of them to stick together was an incredibly inefficient process. They needed a third particle, perhaps an electron, to briefly carry away the binding energy, allowing them to form a fragile union. This was a slow, stumbling dance in the dark. The central mystery is understanding the precise thermal pathway this gas had to follow. How cold did it actually get? The cooling power of molecular hydrogen is not like a modern refrigerator. It has a very specific signature. It works best at cooling the gas from temperatures around 1000 degrees down to a couple of hundred degrees Kelvin. But below that, its efficiency plummets. This creates a theoretical temperature floor, a point below which the primordial gas simply could not cool further. That minimum temperature, likely around 200 degrees Kelvin or minus 100 degrees Fahrenheit, set a fundamental limit. It dictated the final internal pressure of the cloud, which in turn directly influenced the mass of the star that would form. A warmer cloud has more outward pressure, requiring a more massive cloud to overcome it and collapse. A colder cloud with less internal pressure can collapse into a star of a lower mass. So the inefficiency of molecular hydrogen cooling may have been the very reason the first stars were so colossal. The gas could only get so cold, and therefore only the most massive clouds with the most overwhelming gravity could complete their collapse. This thermal struggle imprinted itself directly onto the first starlight, determining whether the cosmic dawn was illuminated by solitary titans or a broader spectrum of suns. The quest to model this ancient cooling process is a race to understand the universe's first and most fundamental recipe for building a star. The formation of the first stars was guided by a whisper from a realm beyond our current understanding. Those initial quantum ripples, the seeds for all cosmic structure, were born in the universe's first fleeting moments during a period of hyper-expansion called inflation. This is where our two most successful and yet utterly incompatible theories of physics collide. Einstein's general relativity beautifully describes the force of gravity and the large-scale structure of the cosmos, the stage upon which everything plays out. Quantum mechanics, with its probabilistic rules, governs the bizarre and tiny world of particles. For a fleeting instant during inflation, the entire observable universe was smaller than a single atom, a domain where quantum rules should have been paramount, yet the gravitational field was also intense. To truly understand the origin of those first density fluctuations, we need a theory that successfully unifies these two pillars of modern physics. The first stars are not just an astrophysical puzzle, they are a potential testing ground for a theory of everything. Consider the very moment a primordial gas cloud began its fatal collapse. As it shrank toward an infinitesimal point, the densities and energies involved would have become unimaginably extreme. Could quantum gravitational effects, phenomena we cannot yet describe, have subtly influenced the final outcome? Perhaps the spin of the resulting protostar, or the very likelihood of it forming a binary companion, was imprinted by these fundamental processes. We are searching for the fingerprints of quantum gravity in the grandest structures imaginable, using the first stars as a cosmic laboratory for physics at its most extreme. Every map of the early universe, every pattern of ancient galaxies, carries within it the hidden signature of that primordial union. Unlocking it would not just tell us how the first lights ignited, but how the very fabric of reality was woven at the beginning of time. Our very existence hinges on a delicate cosmic balance set at the very beginning. This leads us to a profound philosophical mystery, the anthropic principle. It asks a simple yet staggering question. Why did the universe get the recipe for the first stars so precisely right that we are here to talk about it? The entire chain of events, from the first flicker of light to the planet you live on, was dictated by the fundamental constants of nature. These are the unchanging numbers that govern the strength of gravity, the power of the nuclear force, and the mass of subatomic particles. If any one of these values had been even slightly different, the story of the cosmos would have been rewritten. Imagine if the force of gravity had been just a little bit stronger. The first gas clouds would have collapsed even faster, potentially forming stars so monstrously huge they would have burned out in an instant, leaving no time for planets to form. Or if the nuclear force had been weaker, the fusion hearts of those first stars might have sputtered and failed, never forging the carbon and oxygen essential for life. The first stars had to be massive enough to create a rich variety of heavy elements, but not so massive that their pair instability supernova completely sterilized vast regions of space. They had to produce just the right mix of carbon, oxygen, iron, and other elements in proportions that would allow for rocky planets, liquid water, and eventually living organisms. Is our existence, then, just a fantastically lucky roll of the cosmic dice in a multiverse of infinite possibilities, where most universes are barren and dark? Or does the fact that we are here to observe it tell us something profound, that the universe is in some sense tuned for complexity and life? The first stars are the foundational link in this chain. Their specific properties, born from those perfect constants, were the necessary first step in a 13 billion-year journey that leads directly to you. The final frontier in this cosmic detective story lies not in the distant past but in our immediate future. We are on the cusp of a new observational revolution, one powered by technological marvels designed to finally witness the dawn. The next generation of telescopes will be our time machines, built with one explicit goal: to capture the light of the first stars and galaxies. The Nancy Grace Roman Space Telescope, set to launch in the coming years, will act as a wide-angle cosmic surveyor. While the James Webb Telescope peers deeply into tiny patches of sky, Roman will take in a grand panoramic view. It will scan vast swaths of the universe, hunting for the rarest and most distant objects, including the brilliant but fleeting signatures of pair instability supernova from the first stars. Finding even a handful of these unique explosions would give us our first real census of the primordial giants. Then, on the ground, the extremely large telescope will rise from a Chilean mountaintop. With a primary mirror stretching nearly 40 meters across, it will gather more light than any optical telescope ever built. Its incredible resolution will allow it to dissect the earliest galaxies we find, to see if their light is dominated by a few brilliant points, the individual population 3 stars shining within them. It is the difference between seeing a distant city as a blur of light and being able to pick out its brightest streetlights. But what if even these giants are not enough? The ultimate dream is to directly image a single first-generation star. For that, we may need to think even bigger. Concepts are already on the drawing board for telescopes that could one day be built on the far side of the moon, using the lunar surface as a stable, radio-quiet shield to observe the universe's most ancient light without any interference from Earth. Another possibility pushes the limits of physics itself. The formation of every one of those first stars was a cataclysmic event, generating a torrent of subatomic particles called neutrinos. These ghostly particles barely interact with matter, streaming through planets and people as if they were not there. A background sea of neutrinos from the cosmic dawn should still be washing through the universe today, an incredibly faint fossil signal. Detecting it would require a neutrino observatory of almost unimaginable scale, perhaps using an entire planet as a detector. While this remains a dream for the far future, its mere conception shows how far we are willing to go to answer these questions. The quest to find the first stars is more than an astronomical goal. It is a fundamental human drive to understand our own origins. Every new telescope, every technological leap, is a step back in time, bringing us closer to that singular moment when darkness first gave way to light. The mysteries of the cosmic dawn are not impenetrable. They are simply waiting for the right light to be shone upon them. This journey through the cosmic dawn reveals a universe of profound and interconnected puzzles. The birth of the first stars is tied to the nature of dark matter. Their violent death seeded the elements for life, and their collective light sculpted the galaxies we see today. Each mystery, from the missing satellite problem to the source of reionization, is a single thread in a grand tapestry depicting a cosmos in its most dramatic and formative years. We are living in the golden age of cosmic archaeology, where powerful new telescopes and sophisticated supercomputer simulations are bringing these ancient events into sharper focus than ever before. We are made of the ashes of those first magnificent giants, and we now possess the extraordinary ability to turn our gaze backward and ask how we came to be. We have traced the entire arc of existence, from the first quantum whisper to the conscious mind contemplating its own origins. Which of these 30 mysteries speaks most deeply to your own sense of wonder? Share your thoughts in the comments below and subscribe to continue exploring the greatest wonders of the universe with us.